Alright, we're going to finish Module 2. We're going to repeat a little bit about what happens we're going to go over exciting a core, putting a current into a core that is an AC current. So I've got a core sample in this case. This is what I'm going to call it because if you actually go down to Chicago area, Chicagoland, some of the houses that make magnetic cores are down there, and there are a number of test houses down there. I went once and I saw them, how they set up, I believe it's called an Epstein test setup, where they take a core sample and they apply an AC, variable AC voltage, which puts a current into the coil, and then they excite a flux in the coil, an alternating current flux, and then they're able to derive the BH curve from this test. And we're going to actually describe that test right now. But before I do that, let's just imagine that we have the same situation that we've been talking about, and we have now a current, but the current is varying with time. So you can say I've got a current IT. It has some peak magnitude, I peak, and it has, I'm going to use the sine term here, and I'm not going to worry about anything like power factor or anything like that. Just going to point out that we have a frequency that is being applied to this system. And give me one, I gotta move over to my notes so that I don't make any mistake in describing this. Okay, so we know that we are getting, we're applying essentially an MMF to this core. There's so many turns, right? And so what you really do have is you've got an AC MMF, N times I of T. You have a equivalent magnetic circuit, N times I of T. There's reluctance, it's just the core reluctance, and then you're going to end up with a flux, and say it's an AC flux. That was the symbol we decided we would use for that, varying with time. So this AC flux that varies with time would look like, would be this expression here. I'm writing it myself because I was showing it from some notes from the book, and I didn't like they were using a max instead of a peak, and that's very deceptive here. So we would actually end up with a peak flux in the core times omega ET. So what's happening is the flux is going flowing through this core, say in one direction when it's positive, and then it's going to swing back around and flow in another direction when it's negative. So it's going back and forth and back and forth, and it's sweeping up to plus phi peak and down to minus phi peak. So what you have is it's sinusoidal excitation. I cannot draw a sine wave very well here. Okay, so there's one cycle of it. Phi peak minus phi peak. We also know that the flux density in the core, B, is going to be equal to whatever the flux is. So we can have a B of t being equal to the time varying flux times the area of the core. Or, no, I'm sorry, divided by the area of the core. Okay, so you've got the flux divided by the area of the core. Another way then to write this flux density expression would be phi of t equals area of the core times B peak sine omega et. Notice that I've always got sines. I haven't done any derivatives or integrals or anything, so it's just scalar multiplications or times this, and this is what we've got so far. So we're going to work with this to begin with, and we are also, when they set up the test, they put another coil wrapped around this, and I'm trying to use my right hand rule, right? So I'm going to have my right hand rule so that I have if I did put a load on it, I'm going to put the flux in the other direction. So the current, if there was a current, it would go this way. But this is just me wrapping my coil around it and figuring out, where my two ends are and how my voltage is going to be oriented. So you can actually, because of Faraday's law, you can find a voltage across a second open circuited winding. And in a sense, what we're showing right here is the introduction to the transformer section. This is your very simple open circuited transformer as well. And what this voltage here, E of t, is from Faraday's law, would be the derivative with respect to time of let's call this having, this we'll say is N1 and this is N2, and so it would be the flux that linking to coil 2 from coil 1. So I got the voltage here, E of t. E of t is equal to the derivative of N2 turns times the flux that was due to coil 1. We could even call this I1 if we want, so that would be a phi 1 of t. And what that is the derivative of N2 times the area of the core times the peak flux density times the sine of omega t. I'm going to call this omega sub et. So as you recall, that's the electrical frequency that is applied. So it's 2 pi times Fe, so Fe might be 60 hertz if we're in the United States, or 50 hertz if we're over in Europe or somewhere else that uses 50 hertz. Okay, so if I take the derivative of this, I mean, all these terms, these constant terms, fall out, and so I have going to pull them out of this. N2 times area of the core, and since I take the derivative of a sine, then the omega e is going to come out on the outside of that. B peak cosine omega e t. So that's the voltage that I'm measuring on the other side of this. And now what I am always interested in is RMS, because the easiest thing to do, as opposed to just trying to look at a scope, is to put a voltage meter across here, right? So you got some meter like a Fluke RMS meter, or you might have this instrumented up with Yokogawa power meter or something like that, to look at voltages, currents, and they're going to all be measuring RMS quantities. So if I'm going to plug this into here. I know I'm kind of going through this a little bit slowly. I apologize if some of you are like, okay, get to it, get to the point. Okay, so it's 2 pi n2 AC Fe cosine omega et. Now, one last step to get the RMS. It's going to be the peak divided by square root of 2. So ERMS is going to take this whole thing here and divide it by square root of 2. So that ends up being square root of 2 pi Fe. Now I'm just going to make this general. The number of turns involved, area of the core, and I left out B peak up here, times the B peak. Now I'm going to tell you this expression here that I'm going to put a big box around here, because this means it's important. When you take your tests, you want to have this in your notes. This is probably one of I'll say the most important equation of this whole class. I had this on a little sticky note up above my desk since I started my career in 1990 as an engineer, and it's probably still there. Okay, of course now it's like I can just derive it, but this is a formula that's used in a lot of places when it comes to magnetics design, and that's that voltage when it comes to this test that we're going to do. So if we go down to thinking about using the information that we have for a test, we're going to be we want to generate a BH curve, and we know that the units of the H are ampere turns per meter. We know that from Ampere's law that this is N times I divided by the magnetic path length in the core. And so the current, if we say I'm going to put a time domain current into this thing, then we can produce what's on the x-axis. We know that the ERMS is equal to square root of 2 pi Fe area of the core n B peak, which is the peak, and imagining again, let's go to this picture right here, that you simply have another a proportional sine wave. So there's your B peak and your negative B peak here. So flux and flux density are proportional to each other, and knowing all this information with the Epstein test, this is a constant. You have control over the turns in the core area, and so you can pull B peak out of this whole thing, or you could just say B peak equals E RMS divided by square root of 2 pi Fe area of the core turns. And now you know. And so so you're going to use the B peak, you're going to apply the H, and the HP, and I'm going to actually show you now what's happening in the material. So recall that when we introduced ferromagnetic or ferrimagnetic material, that if we had a little sample of material right here, a little cutout of the material, we would have these magnetic domains, each containing randomly oriented dipoles. So you have a test sample that has not been subject to any current thus far, and what you do is you're applying a current, and you're actually taking a setup that looks like this to give you the whole picture. You've got a variable voltage source supply like a variac. You might have some current limiting resistor in front of this. As we will learn, the winding itself is going to limit the current because the winding has an inductance, and it has also a resistance in the windings. But what you have is, this is an electrical circuit for the primary voltage that was just applied to the core. There's some resistance of this primary winding, and there's some, as we will learn, inductance associated, and we're going to talk about this a little bit later. And this then is going to give you the current I1 of T that's going into this core structure. So electrically, this is what the circuit looks like for this test. You're applying a winding current here to a core, and you're measuring a voltage on the secondary side. So it's like you have N1 turns here and you have N2 turns here. You actually have what is a transformer. So this is actually the very first part of module 3 on chapter 2 on transformers. And you have a voltage across there, and you have N1 turns here and you have N2 turns here. So the electrical setup looks like this, and the physical setup is what you're seeing below here. So the current is going to increase, and it's going to follow a path that I'm showing. This green line here, as the current increases, starts at 0 and it goes up, and hence the magnetic field intensity in the core increases, and then it's going to hit its whatever, I'll call this the H peak that's resulting from the current. It hits that point, and then it starts to go in the opposite direction. Well, what's happened is, as you are putting some flux into this core, you're starting to move these guys, these magnetic dipoles, and now you're going to go back in the other direction. So you're going negative current, and this thing, this material can't remember where it started. It's going to go, it's going to start to knock these guys back in the other direction. So it's not going to follow the exact path back here. It's going to follow a different path in this direction as it's going down. And and it will have gone up to some level of B, I'll say B peak 1 here, and this is H peak 1. It won't get to 0 until you apply negative H. I'm sorry, this would be here, H peak, I'll call this H peak 0. It won't get back to 0 until you get to this value negative H peak 0. And now the current goes negative, and this would be negative H peak 1, and that is an exact reflection of what's happening on the other end in the positive quadrant. So here you've got positive H, you have negative H and negative H, and you're passing through these other quadrants on the way. And if you don't change the setting of your test, so you've got this little box, with a variac, and you're turning the knob, right? If you don't increase that value, it's just going to keep going around here. Is there any questions about that so far? Is everybody with me?
Yeah, I just got one quick question. Is this kind of like a hysteresis curve?
Exactly.
Okay.
We are creating what's called a hysteresis curve. So I was trying to build up the suspense here, but that's no problem. In fact, that's good. It's a hysteresis curve. So now you dial up to another value of current, and what's going to happen? Just think about the current. You started. Your material has reoriented these things, and it's starting to push these dipoles. Well, it's kind of mixing them all up a bit. And now, but you're going to, if you repeat this process, it's going to look, it's going to stay on this contour. If you increase to another level, well, let's say that we increase to this H, so I've just arbitrarily picked these. This was the current that corresponds to this point on the curve here. This is the current of your peak. So if I went to, say, another peak here, H peak 2, I'm going to end up hitting another point, and I'm going to have a similar point in the negative direction, and I'm going to have a hysteresis curve around this whole thing. And it's really just going to follow a similar type of contour. And so there's your next level. If you can increase to another point, you're going to get another level here. Now we've talked about a BH curve and shown you what that looks like. So when we introduced BH curves, we gave you this, and I pointed out in the lecture, I'll go to show you this picture right here. I pointed out in the example that I recorded, this is a BH curve, a typical BH curve for it's called M5 grain oriented electrical steel right here. Notice that this is the linear region of the curve, this is the knee right here, but it isn't a straight line. That's because the x-axis is in log. It's a log x-axis, and just not to be confused by that. But in order to avoid that confusion, I'm going to draw it in a linear axis. If we have not hit the saturation point in the material, then it's a line. A linear line is the curve that we produce and that we look at. What is this curve and how does it relate to this curve? That was always a question I had in my mind. It is these points. I didn't really do this. Well, it won't be an exact straight line anyway because of the nonlinearity of the material, but it's close so far. I'm assuming that so far we're unsaturated. We can still put energy into this thing and affect a change in the core dipole moment directions. But at some, okay, so the core, so this is the points, the apex points that you're getting. At some point we're going to be putting more H in, and these dipoles are going to be lined up, so they're going to be pointing in the same direction. At that point you've saturated the core. So kind of draw the picture of a better picture here, right? Here's your core material. And all your dipole moments are lined up. And here's your picture where they're still kind of randomized. They're kind of moving in the direction, but they're still a bit random. Okay, so that's unsaturated. Let's say it's this region right here. And when we're completely lined up, we're going to be in a situation where, give me a moment here. We'll be in a situation where the points, we don't affect a lot of change in the B, and those, see, this would be like you'd have to put a lot of current, hence magnetic field, into the core, and you're not getting a lot of B out. And so you're saturated at that point. And then you get this knee area here. So this is the saturated. And then you've got your knee point here where you put about as much as you can into this. And normally if you're going to design something, you want to design to the knee point as the point at which you're going to get the maximum the B max. So I would call this is why I don't like using B max. I would call this B max. That is my target B that I want to operate at in this whole thing if I'm going to do a design with a particular core. Now okay, so I'm going to show you what clean up the picture here. This is your BH curve then. This is what I would call B max. And there will be data sheets, and I've actually put a number of them up on Canvas that you can look at for different core materials, and they have different BH characteristics. Do you guys have any Do you have any questions about anything I've said so far?
Pretty good so far.
Okay. All right, let's do one last point about what happens when we are hitting saturation. Something's going to change electrically. And this is a point, I think it's an important point if you're going to try to think about the physical meaning of what you're seeing in the curves in the data sheets and what that means with respect to, say, the current that you're putting into the core. And there's a very good example in the text that explains when you hit saturation what happens. So notice what this curve here, and I didn't want to try to reproduce it, is showing me that I'm at a point of my hysteresis curve here. The current's coming down, right? And then the current's going up like this. And what this represents on the x-axis is a peak current. It's an instantaneous scalar value of current at a given point in time. So what it's telling me is that this flux right here, which is proportional to the voltage, proportional also to the flux density, that if I have a zero flux and I'm operating on this curve, this is the saturated curve. So what this corresponds to is one of these points here, not one of the points down where I was in the linear region. What it's telling me is that when the flux is zero, the current is not zero. So this point right here corresponds to a non-zero flux. Here's the current right here that I've just highlighted. So that point, draw a circle around it, is this current here. So what I'm doing is I'm translating what I'm seeing in this could be BH or I flux. They're proportional to each other. Translating it over to the time versus the amplitude. When I go, so I follow the coming back, I've come up to my peak right here, and I'm going back, and it highlights another point right here. This point is that flux here, and I'm going to highlight in green. The flux is green. It's the same, really corresponds to the signal that I'm looking at here, and but the current corresponding to that point is nearly zero. It's and so what it means is that the current is actually becoming very distorted as a result of going into saturation. It's not a sine wave anymore. If I was operating down in the linear region, what that would mean, I would be down at a point, let's say right here, and a point right here. You can see those points. I would be going around this little teeny circle that I was showing you here. If I were at in that linear region, the current would be looking just proportional here's your period. Try to draw this. This is this point here of flux. That's that flux, and the current peak down on the x-axis is what I'm highlighting in yellow, the dot here, and it would line up with the flux density peak that I'm at, which is, let's say that the flux density looks like this. There's your flux density, and let's put in a different color, the current in orange there. And so they're both sine waves. But as you start to become more saturated, the point of this is that the current becomes distorted, and it has other harmonic components in it. Now, my takeaway from this, first of all, is that saturation affects the electrical signals of that are in the magnetic structure. What is it really affecting? It's affecting the current. It's affecting the MMF. It's not affecting the flux. So that's number one takeaway. Okay, the saturation affects the current waveform and makes it less sinusoidal, and we would call this distortion, or having more harmonic content to it, poor power quality. It does not affect the voltage or the flux. Number two takeaway from that is if we're looking at designing something and we're trying to draw correlations between what we think these signals look like and the points that we're measuring on a BH curve. Once we get into the saturation, everything becomes very nonlinear. So in saturation, you're in a nonlinear situation. So rather than trying to understand or replicate this curve that I have highlighted in blue, right, the current there, and see how important that is to my design, I'm actually not going to worry about it. I'm going to use my data sheets, because my data sheets are giving me the information I need when it comes to H. So I will use my H according to the data sheet and trust what it is telling me. So essentially the takeaway I have here is use your datasheet curves, especially when you're starting to operate out in these regions here, because all the information that you're trying to get at is buried inside of this line that we're looking at. And then there's other data that we get associated with losses. Any questions on this? And I'm going to go into losses next. Quiet, so I've probably beaten this to death. Okay, so let's talk about losses. Hysteresis curve of the B and the H corresponds to loss in the curve. And really what it is it's an energy. So we'll in this class we will be referring to magnetic energy as W, meaning the energy. And most of you know in the electrical world, you have losses, right? When we say losses, we mean stuff that you can't use, but it's making heat. For example, you have I squared R loss, right? And that's a power. We also would think of losses in terms of a power as being equal to a voltage times a current. But in the magnetic world, we think of things in terms of an energy, a W, as opposed to losses. And it really has to do with the BH. It's saying here's the H right here, and if you do a closed contour integral of the B, that is proportional to the energy. So as this curve widens, you increase the energy. And this energy is a loss. It creates heat in the core. And it's called, we have what's called hysteresis loss. And hysteresis loss corresponds to the area inside this BH characteristic. More area, more loss. These electrons pushing around these dipole moments have to travel more distance around this contour, and that means it's more lossy. So essentially you've got, I like to think of it as number one, more travel distance, if you didn't have hysteresis, you would, and you're trying to get to this point and this point, you would just travel between them, right? And there wouldn't be any area. That's like no hysteresis loss. So the wider the curve, the more loss. Number two, the faster you travel, you also get more loss. So these two things give you more loss. So I have a question. What makes you travel faster around this curve? It's the distance you traveled, like you're going from point A to point B,
Wouldn't it be
and the
wouldn't
speed. Yeah, go ahead.
Wouldn't it be wouldn't it be the current that you're pushing through it?
Not the current, but I mean, all the current that you're pushing through is proportional to the H. Okay, so H is proportional to I. So it's not that, but it has something to do with the current. Any other ideas? What makes the current have to go faster around that curve that we're showing? We're really looking at what we're used to seeing, say, on an oscilloscope, a different way, but because we're not showing the time. But imagine that the rate at which you travel around this curve is increasing. What is that? Any other guesses?
Frequency?
Yep, that's it, frequency. So that means, so the more you travel is the I amplitude, and the faster you travel is the, let me put it this way, okay? I amplitude is I peak, right? And the faster you travel is the electrical frequency, Fe. So the higher the frequency, the more the losses. Losses go up with frequency. Now there is another, so this actually is a factor in selecting what kind of core material that you're going to use. If you are, and before I talk about another aspect of loss, I'm just going to show you this and then we'll come back to this again. So I'm going to draw a dark green curve here, if I can get this pen to work. That looks like this. And this is a typical characteristic of ferromagnetic material. For example, steel, met glass. These are some of the ferromagnetic materials that you would encounter. Now I'll use a lighter green. I'm going to draw a different hysteresis curve. This is a characteristic of a ferrimagnetic material. For example, ferrites. And another one is mu metal is the name that they call it. Okay, so I'm going to tell you this, then we're going to go back and look at one other thing. Imagine the fact I have a core structure and I'm putting the core into it. Now what we will learn in this class is that you put the current in to get some work, some function, work or function out. The work, the thing that you're trying to do with this, or function, is proportional to the voltage, or the B. Okay, so the The B is what you're trying to get. The H is what you're putting in. So remember that. So if you had to put more current in to get less B, then you're creating, and there's more losses, then you are, maybe you need to change something. Now, if you have the current that's going into this core, and it's an AC current, a core material is a conductive material. It's not a great conductor, right? This is copper, and just in general, we're saying that this is iron. They both can conduct current. So you could imagine that if I were to slice out a piece of this iron and look at what's going on in the iron because of the current, and I apply right hand rule, remember I've got my thumb wrapping around this thing, I've got the flux going in this direction here, I've got my currents traveling around in this direction through the turns, and it's going back and forth. If I have this cross-sectional area like this, and I'm wrapping current to get a flux, what's going to happen is, by another law which it's called Lenz's law, it's almost like a conservation of energy law. Which says that for any current in, you get an opposite opposing current. Opposite opposing current that is induced in a conductive structure in the vicinity. Okay, so and it has to be moving. It's got to have a derivative involved here for Lenz's law to work. So the current has to be going in both directions. What this means is that there's going to be a current induced in the iron itself. Has anybody heard of this before and know what that current might be called? The current that flows in the iron?
Those are eddy currents, aren't they?
Yep, that's right. That's eddy current. So here's another loss component that we have to be concerned about. So we really have two core loss components. One, we have hysteresis loss, and two, we have eddy current loss. Now what eddy current does, to think of this in terms of these green curves that we're talking about, is that the eddy current widens the curves. That's what its impact is. It increases the amount of energy. So what you want to do to deal with eddy current is, what do you do about it? Well, if you've got a sample of core material, so what do we do about eddy current? If the current is flowing around a material like this, we could reduce that if we were to slice this material up. So if I were to take the iron material that I'm showing right here and slice it and then put it back together again like this, then what I would do is I would create little eddy current. The eddy current paths would be flowing in these slices, and it would reduce the eddy current. Okay, so basically these are laminations. They break up the eddy current and they reduce the loss associated with it. And so this is what you do if you're going to operate with alternating current in these cores, is you need to somehow break up the iron and put it together, and then put it back together again.
Just a quick question.
Yeah.
Would all those little eddy currents just eventually add up and sum to that single eddy current initially before it's broken up?
They will end up, what you're doing is you're actually, think about this, I equals, it's similar to this, V over R, right? So
Mm-hmm.
there's a resistance. And so if you say there's a voltage potential across the, there's a voltage here, and there's an R associated with the material. So you have a voltage associated with that current, but the combined R of this is much greater. So what you've done is, if you increase R, the I goes down.
Gotcha. Okay.
Yep, that's what it does.
Yep.
It's really increasing the resistance of the flow of current significantly.
Mm-hmm.
And so it makes it possible. And this is a picture of what we're talking about, the laminated steel. This is typically what you do with ferromagnetic material. Now there are also other types of core materials, but this isn't a materials class. But I want to point this out. Ferromagnetic is typically what's used it's referred to as powdered iron. Instead of laminations, what they do is they grind up the iron and then compress it back together again. So they start out with a different makeup of the material, and then the process of dealing with eddy currents is different also. It's grind the iron up, and so what it'll tend to be is a solid core material, like what we're showing here, like this little E shape, but you buy it as a solid, but it actually molecularly, there's less iron in here than there is in here, because there's a lot more. So the other thing is this: what does this do to? There has to be a downside, right? What is the downside to reducing eddy current through laminations or powdered iron? There's a downside. So recall this, that the work that you want to do is proportional to the B in the core. And what is B in the core? B in the core is equal to the flux in the core divided by the area of the core. And the this area here is the active area that is used um, to allow flux to flow. It's the active area. Now what happens is when you break, if you have laminations, for example, the physical area, here's the area of the core. It would be this cross section right here. This is the without laminations. That's the physical area, would be the product of, say, this W, and we could call this L. So that would be AC equals W times L. That's the physical area that you've got to work with. And if you had less area, then you're going to saturate the core sooner. And it's all about not putting too much current in and getting more out. If you were to laminate this core, what you did was to get for the same physical core area, and you press these guys together, you have the same W and you have the same L. And actually, I'm going to go back here a little bit. This is L and this is W. The way I drew these laminations. This is L and this is W. So the laminations stack up in the L direction. And that corresponds to, if I look at this picture right here, what I said was I've got L, and then the physical area of this is L, and the physical area across here is W. Or it's not that, take it back. The physical area is one of these legs, W. That's your core area. You have W here. So you have L and W, and so the physical area equals W times L. But the active area, going back to this, for the same physical area, active area is reduced. That's because what's happened is you have introduced air in between. There's air effectively in between those laminations. And for the same area, you get less physical because just the process of putting together. And so what it means here is that the length, the active length, I'm going to call that L sub s, the stack length, is less. And so what I'm saying is the physical area of the core is W times L. The active area of the core is W times L sub s, where Ls is equal to something we call a stacking factor times the physical length. So the Ks correlates to the lamination thickness in steel, the ferro, or it correlates to the manufacturing process of the ferry type materials. What this means then is that your area of your actual area of the core that you can use is going to be equal to Ks times W times L, where L is the physical length, or that's equal to width times the L sub s. If the laminations are thinner, more of them, you get lower loss, but you also get a lower Ks value, and you get less active area. So Ks is going to be less than, or it's going to be less than 1. You never have any magnetic material that has a Ks of 1. You will always have a stacking factor, and you'll notice this is the last point in the homework. You'll notice this in one of the homework problems, I believe, that they give you a stacking factor. We actually have two factors, right, that we talked about. Remember, we have the fringing factor, Kf, that makes the gap area bigger. Well, the stacking factor Ks makes the core area less. If people forget this on a test, it's 1 point off, okay? So you need to pay attention to fringing. If you forgot that I said there's a fringing and I've said there's a stacking, and you didn't take those into account in calculating your flux densities, then if you missed both of them, that's 2 points off of an exam question. Just to give you, it's important. Now what happens is, typically the ferro materials are going to have a Ks anywhere from between around 0.9 to 0.8. The ferry material is going to have a Ks of probably less than 0.8. These are again just rule of thumb experiential factors that people know. We're not getting into all the physics of it. Okay, is there any question about this? Because we're now at the end of our time. but I want to make sure everybody's clear on these 2 points. No questions? So I got to ask you a question. If I had a higher frequency that I'm applying to my magnetic component, what do you think I want to use? Ferromagnetic material or ferrimagnetic material?
You would want to use fairy magnetic materials, right?
Yep. So like a ferrite. Another question. Remember, the work is done by the flux density. So for a given, the whole goal of magnetics design is to get a magnetic component to work that is as cheap and as small and as light as you can possibly get it. And you want it to also be efficient. So if you want if you use a ferrimagnetic material and you are really and you're trying to do a certain function, a certain amount of work, do you think the ferrimagnetic core is going to end up being bigger or smaller than a ferromagnetic core?
Bigger.
Bigger, right. Now, why? Let me ask this: which would have the higher knee point on the BH curve? Going back to the BH curve picture we had, ferry or ferro? So this is the design point here. I want to get as high as I can. Which one will be higher? A ferro or a ferry?
Ferro.
Which one? What was that?
Ferro.
Ferro, you're right.
Ferromagnetic.
That's right, the ferromagnetic material. And if you look at my problem examples I posted, I go into this a little bit. The ferromagnetic material is typically going to be B max. One last point, if you guys can just be a little patient. B max for ferro material, steel, is going to be anywhere from 1.5 to 1.8 Tesla. The higher up you go on the curve, the more lossy the material is. This will be thicker lamination, and this will be thinner lamination. B max for ferry, most common one is ferrite, is between 0.2 and 0.4 Tesla, depending on the manufacturer. So you pay a heavy price for using ferrites. So you better make sure that you've got a good reason. The thing is that the ferrite's gonna have much lower high frequency loss than the the steel lamination material. So you have to be very careful. There's some other materials like met glass. This is one that it's kind of a in-between material, and I did most of my career was with the Navy, working on Navy ships where cost is not as big of an issue. Things like efficiency, power density, low acoustic noise, these were more important things, and so we used met glass for almost everything we did. There's some other core materials, but it falls more into like a ferry, but I don't think it's either a ferro or a ferrite. It's called nanocrystalline material. And what the nanocrystalline material does is, instead of the lams being pressed together, it's like a coil of metal where the flux lines would go in the direction of these coils. And so typically it looks like a circle, a bunch of coils. These are very, very low loss, and they're used for EMI filters usually. Okay, I think we're at the end. I went overtime. I apologize. We did cover a little bit of the transformer, and we're going to be full on into transformers in the next three lectures before the exam. Any last final questions? Or
For the last two homework question, uh, you said you did some examples about those. If you did, where we can find
I
them,
put them on
and
the
if
video that I posted. You remember I said I was going to do a video of taking you through a couple examples.
so you are they in the Canvas or they are
It's in
somewhere else?
Canvas. I just posted it just before class.
Oh, I see.
So it should be available. Go up there, you'll get
All right.
a link to it. It's on the YouTube channel there.
Oh, okay. So let's say if they weren't enough, if I have more question, you point me somewhere in the book, any section in the book that you think they'll be helpful?
The book examples, like I said at the beginning of class, the book examples is what you really want to look at because they're all helpful. Every one of those example problems. In fact, if you want to do a good job of studying for an exam, make sure you can work all the example problems in chapter 1 and chapter 2. And then you're going to be in good shape. The examples are really good. But I try to provide some more insight with this video lecture. Usually I can go faster in the class and I give you more examples in class. And I will post the notes from the example, but they're messy, okay, because I did them as I was talking about them. So I recommend looking at the video and the note together. I'll put the notes up right after class.
Okay, thank you.
Yeah. Okay, well, hang around here in case there's any other questions.
Would you mind going back to slide 13, please?
Sure. Yep. Okay.
Thank you.
We don't talk about Lenz's law in detail. This is probably the only time I'll talk about it, but basically, you think about a AC current wrapped around a conductor, you're going to induce a current into the conductor. That's really what Lenz's law is. It's kind of like Faraday's law, but it's purely electrical. Faraday's is the connection between magnetic and electrical connection. That's why it's so important.